All right, today we are going to talk about dot products and work. All right. We've been doing work, but we're going to do some physics work.
I thought this was PreCalculus.
Well, you know what? It's a beautiful thing when math and science can intertwine, right? Yeah.
So that's where the work comes in.
Yes, the work. Okay, so here we go. Dot products. We have talked about adding vectors. We've talked about multiplying by a scalar. We can subtract vectors. We have not talked about multiplying vectors. Okay, physics people, do you know what a dot product is? Okay, I don't think that this is something that you do in physics. So yay, something new. All right. A dot product is how we multiply vectors. However, we do not get a vector, we get a scalar or a number. Okay. So here, the dot product, here's my vector u, here's my vector v. When we take the dot product, notice the symbol. Okay, it looks like a multiplication symbol. Okay, but we call it the dot product because it's not really multiplying, because we don't get a vector out of it. Okay. So when we take the dot product, we multiply the horizontal components plus multiply the vertical components. We get a number, or what we call a scalar, out of it. We do not get a vector. Okay. So it's just the sum of the product of the horizontal components and the product of the vertical components. Right? So we're going to do an example. We are going to use these two vectors for a couple different things, so please write them down. Vector v is negative 2i plus 5j, and vector w is 4i plus j. What do you mean? Take the dot product. Take a dot product is, it does not matter what form it is in, because we're just going to get a scalar anyway. Okay? You can write them in component form if you feel more comfortable, but all we're going to do here is to take the dot product. Okay? We're going to multiply our horizontal components. So our horizontal components are negative 2 and 4. So we'll take negative 2 times 4, and then we're going to add the product of the vertical components. So our vertical components are 5 and 1. So our dot product is negative 8 plus 5. Negative 3. And that's it. We're not done, but that's, I mean, the dot product's pretty simple, okay? You just need to remember what do you need to pair up together to multiply, okay? Now I want to talk about some properties on page 460. Okay, we have some properties here of our dot product that I'd like to talk about. The first property is that the dot product is what? What property is this? Commutative. Very good. If we take the dot product of a 0 vector and a vector, what do you think it's going to be? the number 0. This is the vector 0 dot vector v, and we get the value of 0. 3, u dot v plus w, okay? The dot product is like multiplication, okay? So, u dot, the dot product of u and a sum is the same as u dot v plus u dot w. Okay, it acts the same as multiplication would with the distributive property. Okay. Number 4 is a good one. The dot product of a vector in itself is the same thing as the magnitude squared. Okay, let's talk about why that is. Let's say that vector v is AB. How would we take the dot product? A times A plus B times B. A squared plus B squared. That's what's under the radical for the magnitude, correct? So the dot product is the same thing as the magnitude squared. Okay. And then our last property, this is a good one. We have a scalar multiplied to the dot product. Okay? Be careful. This is all multiplication. And so either you take the scalar times u and then take the dot product with v, or you can take the scalar to v and take the dot product with u, but that scalar does not get multiplied to both. Now, yes, you could take the dot product and then multiply it by the scalar, which is probably what you're going to do anyway, especially with the parentheses, but please realize that this does not distribute to both. Okay, same thing as if you had 2 times 3 times 4. Okay, you just do one multiplication at a time. Okay, so in your homework you will get some problems where you'll have to find the dot product. You might have a dot product times a vector, and so you'll be doing some dot products, some scalar multiples, that kind of thing. Okay. All right. Now, the dot product, pretty simple to find. It can be very useful to us. Okay. How can it be useful to us, Mr. Coleman? You're all on the edge of your seats waiting to know. Okay. We can find the angle between two vectors using this. We know that the cosine of theta is the dot product over the product of the magnitudes of our two vectors. Okay. So write it down, and then we'll talk about it a little bit. Now, technically, we can find more than one angle in between two vectors, couldn't we? Okay. Technically, we can find an infinite number. But this is going to find the closest angle. Okay. Why is it going to find the closest angle? Okay, we're going to set this up, and we're going to have the cosine of theta equals something over here. We're going to have to take the inverse cosine to get theta by itself. When we punch inverse cosine into our calculators, what kind of angles do we get? angles from what two quadrants? 1 and 2. So we're going to get an angle between 0 and 180. So it's going to find us the closest angle. All right? Now, if the angle between the two vectors is 0, then that means we have parallel vectors. It doesn't mean that they're necessarily going in the exact same direction. They're either going in the same direction or opposite directions, but we say that they're parallel. Okay. So, the two vectors from our last example we're going to use to find the angle in between them. Okay. Now, if you look back up here to our formula, we need to know the dot product and the magnitude of each vector. We found the dot product already, right? The dot product between these two vectors was -3, correct? Okay. Now we need the magnitudes of each. So the magnitude of V, how do we find magnitude? Square root of -2 squared plus 5 squared, which is square root of 29. And the magnitude of W, I'm going to take the square root of 4 squared plus 1 squared, which is square root of 17. So now, the cosine of this angle in between our two vectors is the dot product, so -3 over square root of 29 times the square root of 17. So to get theta, we're going to have to punch in the inverse cosine of this fraction. Please be careful when you punch this in your calculator. Remember, if you have more than one thing in your denominator, it needs parentheses. Otherwise, it will not do your order of operations like you want it to. Let me know if you have an answer for me. 97.77. Do we agree with Kylie? Everyone can get that in their calculators? Awesome. Okay, let's talk about a special case. We already mentioned that if the angle in between is 0, then we have parallel vectors. Okay? Now you've noticed that as we've gone through these vector sections, we've had some kind of odd vocabulary, right? Instead of like multiplying, we say dot product. Okay. Instead of perpendicular, when two vectors are make a 90-degree angle, we call them orthogonal. Okay. Physics, did you use this word in physics? No. Okay. Orthogonal vectors are perpendicular to each other. Okay, the angle between them is 90 degrees. So let's think about what this means in terms of our formula from the previous slide. Okay, we know that the cosine of the angle in between two vectors is the dot product over the product of their magnitudes. What is the cosine of 90 degrees? the cosine of 90 degrees is 0. So what would that mean about our formula? If I was finding what the angle was and it was going to be 90, what would have to be on the right side? Okay, good. If this fraction is 0, we have the cosine of theta is 0, which means our angle would be 90 degrees. More specifically, if this dot product is 0, the whole fraction is going to be 0, right? So if our dot product is 0, we don't have to plug it into this formula. We know that our vectors are going to be orthogonal. You can plug it into the formula, that's fine, but you're going to do more work for yourself, okay? If the dot product is 0, we have orthogonal vectors. Now, there will be times where I will ask you to decide whether two vectors are orthogonal or not, okay? I know that we are all good at mental math, but I need you to show your work. If I ask you to determine whether vectors are orthogonal, I need you to show me that you found the dot product. A plain yes or no is not good enough, and you will not get full credit for that problem, okay? The minimum amount of work that I need to see would be this. Here I have vector u is 2, -3. Here I have vector v that is 6, 4. So if I want to determine if they're orthogonal, I'm going to take their dot product. So the dot product of u and v. How do we do this? 2 times 6, add it to -3 times 4. What is our dot product? Our dot product is 0. So yes, u and v are orthogonal. Okay. If our dot product is not 0, then they're not orthogonal, okay? But I have to see you set up the dot product so I know that's what you did to find it, okay? A plain old yes or no is not going to suffice. All right. One last thing is the concept of work. We're going to do work to do work here. All right. So those of you who have had physics, you know that work is force times displacement. Okay. Displacement and distance. I know those are very different words in physics. So if I need to change this to displacement, I can. Okay. We're not going to worry too much about the displacement aspect of it. Okay, we're not going to go in a negative direction here in PreCalculus. Okay. But work is force times displacement. Now, what's important about the force is the only component of force that matters is the direction in which our object is moving. Okay? So if I'm pulling something at an angle, but it's dragging along the floor, the only force that matters is the horizontal component of force, because that is what the way the object is moving. Okay? If I'm pulling something at an angle but it's moving vertically, then the vertical component of force is the only one that matters. Okay? The horizontal component doesn't matter. Okay? So when we do force times displacement, we have to make sure the force is the component in which the object is moving. So, I'm going to go through an example. It's actually a problem from your book. So if you want to, either you can open your book and read along with me. I don't think that you should copy down everything word for word. So if you want to just make a note to yourself that we are doing number 72 from on page, it should be like 468 or something like that. But we're doing number 72. That way, if you have questions about the work problems, you can at least refer back to a specific example. Okay, so this is number 72. A tractor pulls a log 800 meters, and the tension in the cable connecting the tractor log is approximately 1,600 kilograms. Okay, 1,600 kilograms represents what? The force. Okay, a weight is considered a force. All right. So the direction of the force is actually 35 degrees. And we want to know the work done pulling the log. All right. So I'm going to attempt to draw a picture here. We have a log. It is attached to a tractor at a 35-degree angle. Okay. There's our tractor. I know that's not really what a tractor looks like, but it's just an illustration. Okay. So we have a force of 1,600 kilograms here at an angle of 35 degrees. And this tractor is going to get pulled 800 meters. Okay. So the work is force times displacement. Now, what is the component of force that matters? Okay, the 1,600 kilograms isn't what I want because our log is not moving along that 35-degree angle. Our log is being pulled horizontally, okay? So since it is moving horizontally 800 meters, we want the horizontal component of force. So our force is not 1,600, it's 1,600 times the cosine of 35 degrees. Okay, that is our force. Okay, our displacement or distance, whatever word you want to use, our log is being pulled 800 meters. Okay, so now you can take force times displacement. Anybody have something for me? Too big to spout off? 1,048,514.62?
Yeah. That sounds
Nope. Okay, let's talk about the label. What's the label for our force? Kilograms. What's the label for our displacement? And we multiply. So we multiply our units. I know it's awkward, and I know you physics gurus, you don't like this kilogram meter. Okay, I know you're used to Newton meters, but unfortunately, in pre-calc we don't always use those units. Yes. Oh, does it? Oh, okay. I didn't know. So it does give you 15,691 newtons, so you could use that instead of the 1,600 kilograms per newton meters. Okay. Okay. I must have missed that when I was writing that in. Maybe I'll change that so I don't upset so many visits. Here's your homework. And look at that. We have over 10 minutes to start our homework. Okay? You have not gotten this opportunity for a while.
I need 11 minutes.
I said over 10. You actually have, what, we're in here till 51, right? You have 14 minutes, according to my watch.
Can't see.
You turn on the light, Carly. Thank you.